So now we're looking at section 1.3, which focuses on slopes, another fancy word, rate of change, and linear functions. So a quick review of linear functions. It has characteristics that are different from other functions. Here, how we can tell that it's a linear function. One, there is only one variable per term. All of the variables only have exponents of 1. You'll not see an x squared or an x to the 1/2 or a square root of x. Linear equations graph lines, and the slope is constant. That just means it's the same everywhere. So now let's take a look at two different equations of lines. The first one is called the slope-intercept. It's with the form y equals mx plus b, where m is the slope of the line, and b is the y-intercept, which would be the form 0b. Second form of a linear equation that comes in really handy is the point slope. We have y minus y1 equals slope times the x minus x1. And again, the m still representing the slope. And x sub 1, y sub 1 is any point on the line. The slope of the line describes the steepness or pitch and the direction. So if you recall from previous algebra courses, we always read graphs left to right. And if the line is increasing or going up, that means our slope is positive, greater than 0. If the line is decreasing left to right, that means the slope is negative. If the line is just horizontal or constant, that means the slope is 0. There is no steepness. And pretend that that's a straight vertical line. That means our slope is undefined. The formula for the slope of a line through 2 points is y sub 2 minus y sub 1. Basically, you subtract the y's and subtract the x's in the same order. So as long as you start from the same point, it doesn't matter. You might also see, delta y over delta x, where it's just representing the change in y or small change in x. We're also going to be working with something called the difference quotient. I'm going to write it in a slightly different form right now, since we're not to the point of using the difference quotient yet. But basically, it's using function notation for the y values instead of the y values. So it'd be like the function notation at x sub 1 minus the function notation at x sub 2 over x sub 1 minus x sub 2. And notice here, I started with x sub 1s instead of the x sub 2s. It really doesn't matter. It doesn't matter because your signs are going to reduce at the end anyway. So just for practice, here in example A, they want us to determine the slope of the line containing the 2 points -2, 8 and 5, -12. So to find that slope, we're going to subtract the y values. Let's say if we started with the second one, that would be a -12 minus 8. But if we start with a second point up top, we have to start with a second point down below. So that would be 5 minus a -2. That minus a negative becomes plus a positive. So we get a -20 over 7. And that doesn't reduce, so that would just be our slope. Now we're looking at the intercepts of lines. So the intercepts of any equation, doesn't matter if it's linear or quadratic or what, but any equation are points where the graph crosses or touches an axis. So in order to find the intercepts, and again, this is of any equation, we plug in 0 for the other variable and solve. So for example, to find the x and y intercepts of any function, particularly this linear function, to find the x-intercept, we are going to plug in 0 for the y. So that would give us 0 equals 3x minus 10. Add 10 to both sides, 3x. Divide both sides by 3, and we get 10/3. So that would give us an x-intercept of 3 1/3 and 0. Now to find the y-intercept, that means our x value is going to be 0, and we have to find what the y would be. So in that particular function value, we would have y equals 3 times 0 minus 10. which would just give us a negative 10, which we kind of knew because notice this is in slope-intercept form, where 3 is our slope, and that 10 is the y-coordinate of our y-intercept. So we get the y-intercept of 0, negative 10. So you just plug in 0 for the other variable. Next section is equation of lines. So to determine the equation of a line, remember we need two things. We need to know the slope, and we need a point. And that point has to be on that line. Now, here's an important note of understanding. You might want to go like this. Okay, that point on a graph represents, or I should say points plural on a graph, represent solutions of its equation. So every solution to the equation is represented as a point on its graph. So when we're looking at y equals mx plus b, remember we usually try to find the slope and the y-intercept, but we leave the x and y as variables. That's because the m is the slope, it's constant, it's not going to change. The b is a particular y value, it's the y-intercept, it's not going to change. But that generic x and y represents all the points on that line, all possible pairing solutions that we have. In example C, they want us to give the equation of the line that passes through 2 points. So remember, in order to write the equation of a line, we need a slope and a point. But we can find the slope since we have 2 points. So let's do that first. Let's find the slope. Take negative 2 minus the negative 4. And 6 minus 5. Remember, minus a negative is plus a positive. So that gives us a positive 2 over 1. So we get a slope of 2. So that gives us y equals 2x plus b. Note, neither of those points is going to be our b. Okay, remember the b is particularly a y-intercept, and our y-intercept is always of this form. That x value has to be 0 for it to land on the y-axis. Neither of those points has a 0 in the x-coordinate. So we have to find the b. There are 2 ways we can do it, using y equals mx plus b or using the point slope. We're going to get the same answer either way. Let's do it first using slope-intercept. So if we get y equals 2x plus b, and we want to solve for b, remember x and y represents any point on the graph. So let's just use this first one, 5, negative 4. So negative 4 for y, 2 times 5, that's b. So we get a y-intercept when we subtract that b from both sides to be a negative 14. But again, keep in mind, they want the equation of the line, not just the b value. So we plug it back in, y equals a 2x minus 14. We plugged in the m, we plugged in the b, and we're leaving the x and y to represent all points. If you guys prefer, we can use the point slope, y minus y1 equals, remember we found our slope to be 2, x minus x1. And then we can use either the 5, negative 4 or the 6, negative 2 for our x1 and y1. And again, it doesn't matter which one. Let's just use the same one again. So y minus negative 4 equals 2 times x minus 5. Subtract 4 from both sides, and hey, look, we get the exact same equation. Now, all of that is probably a huge review, and average rate of change is probably review as well. So we're taking it slow, right? So not all functions, though, are linear, right? So that means their slopes change within the graph. So to find the average rate of change, we find basically the slope between specific or requested points in a function. So the imaginary line that will connect these 2 points, because you're still finding technically the slope of a line. So the imaginary line between those 2 points is what we call the secant line. So in example D, we have this nice little parabola, upside down parabola, and it's asking us to find the average rate of change between the two given points. Now, those two given points are -1, 2 and 2, -4. So if I were to just draw a little dotted line between those 2 points, that is the secant line. And so to find the average rate of change, basically find the slope between those 2 points. So we can subtract our y values. We have -4 minus 2 on top, and then subtract our x's, 2 minus -1. So negative is plus positive. So that gives us a -6/3, which gives us an average rate of change of -2. So right now, it doesn't feel like a whole lot of difference between finding a slope and finding an average rate of change. But it is important that it's a secant line. You're going through 2 different points. Later on, we're going to find the slope at a single point. Okay, at a single point, which is going to be kind of fun. And that's where the derivative comes in. So get used to finding the slope, the formula for slope, and average rate of change. Now, how do we interpret the average rate of change? This is just kind of my own little thing. I want to be sure that you guys have basically 5 things involved when we're interpreting any rate of change, whether it's an average rate of change between 2 points or later on an instantaneous rate of change at a single point. It's still a slope. So the one thing that we need is basically what I would call time frame. In other words, where in this graph or where within this function are we looking at this particular slope? We also need to know what we are studying. Is it the income of your employees? Is it the population of rabbits? Is it growth of bacteria? So you need to focus on what is that output that you're looking at. The third thing is whether or not what we are studying is increasing or decreasing. And then that's where our rate of change comes in, which is basically by how much is it increasing or decreasing, and then your units. And remember, your units, since it is the change in y over change in x, it is your y value per 1x value. So let's do an example. Example E, it says the poverty threshold in the United States was modeled by f of x equals 0.004x squared plus 0.057x plus 1.28. And then the x, your input, is restricted between 0 and 35, where x represents the number of years since 1960, and f of x is the US poverty threshold in thousands of dollars. So a couple of things that's important is years since 1960 and thousands of dollars. So if you see the number 3, that 3 represents $3,000. So they're wanting us to find and interpret the average rate of change between the year 1975 and 1990. So that means we need to figure out what those x values are. And again, when they say average rate of change, I want you to think slope right away. Rate of change, slope. So in 1975, that is 15 years after 1960. So that gives us an x value of 15. 1990 is 30 years after, so that would be x equals 30. So we need to find the slope. Remember, in order to find the slope, we need 2 points. Well, I have 2 x values. That means I need to find their y values. So we're going to plug them in. F of 15. So plugging in 15 everywhere that's an x, that gives us a y value of 3.035. So we have the point 15, 3.035. And now we have to find our next y value for the year 1990. So we're going to plug in f of 30. And that gives us a 6.59 as our y value. So that gives us the point 30, 6.59. So now that we have 2 points, we can find the slope or the average rate of change between those 2 points. So we're going to subtract our output value, 6 minus 5, 9 minus 6.59 minus 3.035 over 30 minus 15 gives us a 0.237. When you are interpreting these, it is good to realize what the units are in that fraction that we just did for the slope. The top was our y values. So that was in thousands of dollars. And the bottom is in years. 30 years after 1960, 15 years after 1960. So those two units are going to come in handy when we go to interpret what this means. So first of all, remember we want the time frame. Well, we are between 1975, 1990, and then what it is that we are studying. Okay, we are studying the U.S. poverty threshold because our slope, our average rate of change is positive. That means it's increasing because remember slopes with that are positive go up left or right. So the U.S. poverty threshold increased. And because it's a secant line, it is an average. It could have kind of gone up and down between those years, but it increased an average of, now remember that 0.237 is in thousands of dollars per year. So if I multiply that by 1,000, that actually gives us $237 per year. You could have written 0.237 thousands of dollars or in thousands, but it just makes more sense in context to make it clear for your reader. So again, we had our time frame between 1975 and 1990. What we were studying, which was the U.S. poverty threshold, what it did, it increased. We knew that because it was a positive slope, positive number. It was an average between 2 years of, and then we looked at our units, the 0.237 in thousands of dollars is equivalent to $237 per year. All right, guys, that's it for 1.3. Good luck. Talk to you soon. Bye.